So we're continuing on in Chapter 10 into Section 10.3. Chapter 10 is about hypothesis testing, and we're looking at two examples. One is to test the population proportion, which we've done, and now we're going to use hypothesis test to test a population mean. Okay, and then we reiterate some of the things we've been thinking about in the past. If an event has probability less than 0.05, we consider it unusual or statistically significant. We call 0.05 the significance level. So we talk about outcomes meeting a certain level of significance. That's a certain level of unusualness. That typical number is 5%. If an outcome seems to have probability less than 5%, we would think it's not likely we should see that event. And then we convert that into this idea. Statistical significance can cause us to doubt how we computed the probability. So we made some assumptions. We talk about an event and its probability. If we see the event and its probability is tiny, like 0.05, then we say that maybe the way we computed its probability is incorrect. So that's one of the founding principles of the way statistics works. If we see something unusual, you're not supposed to see unusual stuff. Therefore, maybe the reason we're thinking it's unusual is incorrect. It's actually a usual value, and maybe we can make some conclusions based on that. A significant result favoring the alternative in hypothesis testing causes us to reject the null hypothesis. So in hypothesis testing, we've seen that we want to see a result that causes us to think the alternative might be true. If the result makes us think is the opposite of what the alternative is, so if we're looking for something to increase and actually decreased, we can't reject the null hypothesis in favor of the alternative. So anytime you are doing a hypothesis test, you've got the null hypothesis, you've got an alternative, and you reject it. You say, I'm rejecting it because I think the alternative is true. You're not allowed just to reject it and say, well, it looks like that was pretty unusual, therefore it can't be true if you were looking for one thing. So if you figure, well, maybe I should be looking for the opposite thing, then you have to construct the experiment over again, and you have to do it again with a different alternative and carry it out. And that's because of the way we construct the p-value or the level of significance. It's dependent on which kind of alternative you use. So if you wanted to be fair and you wanted to make sure you could reject the null hypothesis if anything went wrong, you use a two-sided alternative. And we know how to do that. Statistical significance can be stated in terms of a test statistic or a p-value. So with proportions, our test statistic was either the sample proportion, which you could use in situations, or the z that you compute from the sample proportion. Or in terms of the p-value is this area, either on one side of the test statistics value or the other, or equally distributed on two sides of how far away it is from zero. So those are called the classical, so using a test statistic is called the classical approach. So these kinds of values would be considered unusual, so we reject the null hypothesis, or the p-value, it's the p-value approach. So they're called the classical and p-value approaches. P-values less than 0.05 are usually considered to identify a statistically significant result, but you can use other levels of significance if needed. So sometimes people use 0.01, but 0.05 is more or less the gold standard of what you use, unless you want to be really sure that you haven't made a mistake when you reject the null hypothesis. So if you're just doing an exploratory examination of the data and you get a p-value less than 0.05, then you could say it looks like the null hypothesis is true, and then what conclusions can we draw about that? And then if you want to be more sure, you could carry out another experiment, maybe with a larger sample size, to guarantee you haven't made a mistake. We use simple random sampling from a normal population, and we compute t is x bar minus mu. Sometimes we write mu naught because it belongs to the null hypothesis, over s over root n, to do hypothesis testing for the population mean. All right, and then so we're going to re-examine some of the properties of t that we're going to need coming up. So here we go, facts about t. So t is this computed quantity. You collect data, you compute the standard deviation, sample standard deviation, you compute the sample mean, you put in here a value of the population mean, put the sample size in, you get a t value. And if you've done your work and that mean is the right number, then this statistic follows the t distribution. If that number is incorrect, then we don't have a t distribution. Under the null hypothesis, we're assuming that's the correct value. And so under the null hypothesis, the kinds of values we're supposed to get, we know what they look like that follow a t shape. And we know what unusual values look like in a t shape. And so then, if we get unusual values, we say the way we're computing this must be wrong. If we know we have normal data, x bar is normally distributed, and we know standard deviations from a normal distribution look like what they're supposed to look like for the t distribution. So the thing that must be wrong is we got the wrong mean in there. So we can reject the value of the mean if we get unusual values of t, favoring the alternative. So here are the facts. For z and t are nearly the same if n is large. So remember, z looks like x bar minus mu over sigma over root n. And t looks like x bar minus mu over s over root n. So we're saying if we sample from a normal population and we compute this quantity where we put the actual value of the standard deviation in, or we compute this quantity where we put the value of the sample standard deviation in, and then we look at the pattern of values you get in those two situations. So we know a z gives you a density curve that we've been drawing forever, and t gives you a density curve too, which looks almost the same. And if n is large, it's really, really the same. So z and t are nearly the same if n is large, and the reason for that basically is that the sample standard deviation will be really close to sigma, so you're really computing just about the same quantity. If n is not large, t is a little more variable than z. So that means it's a little more spread out. So over here we know where 0, 1, and so on are. 0, 1, 2, 3, we're familiar with that kind of standard deviation calculation and drawing the graph of a normal distribution in terms of standard deviations. So we would take that same shape and we just stretch it a little bit and stretch the tails out a little bit. That's what t looks like. So by I, it looks almost the same. And it gets a little more variable just because the tails are a little bit longer. Z has one shape and one set of tables that goes with it. So we've seen that before. The Z tables, I've got them here. It's two sides of this one page. T has a different shape for each n, so we need a table for each n. So instead of having a table for each n, I've got here t tables. On one side here, we'll have what's called the degrees of freedom, and across here I'll just have the tail probability. So this will just be critical values for the different tail probabilities. So there is a table that lists all the values like this table does for each sample size or each degrees of freedom. But typically we just use one that just has a list of critical values on it right here. And this is called table 6. And the normal one is table 5. By I, z and t are very similar. We said that. And even the critical values are about the same size. So if I go to look at the normal distribution and say I look at the 5% level of significance, so it's tail probability 0.05, for example, for a one-sided test. Then I get a z value of 1.645. And if I look at that same 0.05 probability on my table of tail probabilities here for t, and I go, say, down to degrees of freedom, we'll talk about that in a minute, degrees of freedom 25, it's 1.7, that's pretty much 1.6. For small degrees of freedom, it gets as big as 2 and 3, and for bigger degrees of freedom, it looks like 1.645 again. So on we go about degrees of freedom. Oh, here it is. Tables for t use degrees of freedom equals n minus 1 instead of n to identify which line in the table to use, which table or line in the table. Yeah. Fine, and we'll be doing that in a second, reading off from the tables. The quantity s over root n is called the standard error of the mean. You might see that in computer output. Sometimes we use the shorthand SEM, standard error of the mean. And finally, t requires simple random sampling, we said that, and a normal population, or a large enough sample. For a large enough sample, of course, t is going to look like z. So with a large sample, you could give up on t altogether and use z in its place, and you'd be fine. Although there's no harm in using t, it's slightly more accurate, you get the same answer. So that's our introduction to, we haven't done any hypothesis testing. We've just written a bunch of stuff down and made a bunch of statements about how hypothesis testing works when you're testing the mean, and how t and z compare, because we've been using z with proportions. Now we use t with the mean. And I guess we're ready to move on to the next slide.